This is the first time in human history that we've really seen every single atom in a molecule. This was published in 2009. There it is. That's the first picture of humanity seeing every atom in a molecule. That's pretty profound. You guys have been alive, you probably haven't heard about this, but that's a big deal. I mean, they've been hypothesizing about molecules and atoms for thousands of years, and all of a sudden we can see it. Another example, X-ray diffraction. So crystals. You guys look at sodium chloride, it's shiny, it has sharp edges, it's crystalline material. What does crystalline mean? You have a repeating lattice of sodium and chloride atoms. It's just table salt is sodium chloride. This is what it looks like. You have a chloride, you have a sodium, back and forth over and over again. Essentially what we can do is take these crystals, put them in the path of an X-ray, and the X-rays get scattered on a plate. It's like taking a photograph except using X-rays. Depending on how they scatter, we can figure out what that crystal is made of. Sodium chloride, not that interesting, right? What about something else, something bigger? Photosystem II, and I'll talk about this a little bit later, but essentially what photosystem II is, it uses sunlight to split water into oxygen and protons. This is an important process. Nature needs to do this in order to survive, but basically it's a protein that does it. If we can make a protein crystallize, much like sodium chloride, with repeating units over and over again, shoot X-rays through it, we can figure out what it looks like. If we know what it looks like, we can figure out how it works, and then we can utilize it for ourselves. We can modify it, we can make it better, we can split water with sunlight. So theoretical. I know some of you guys are in physics yet. No? Not yet. You had chemistry and then physics. All right, that's fair. Well, the excitement awaits you next year. But in physics, basically, so here's one idea. You take a cannonball, you shoot it, right? If you know the velocity it comes out and the angle it comes out, you know gravity, you can figure out where that cannonball is going to land. This is relatively easy stuff. You guys will do this calculation next year. If you know force, velocity, you can figure all this stuff out. We can do the same thing in chemistry, but do it with molecules. And the idea is, going back to BPI platinum chloride, we can essentially use equations similar to these, but completely different because it's quantum mechanics. But it basically describes electron clouds around these molecules and how these electrons behave. And if you know how the electrons behave, you know how the molecules will behave. So here's an example. There are programs now you can literally draw these molecules in a computer, click a button, and it'll do a calculation. My buddy Luke that I mentioned earlier, he's an expert in this. This is all he does. He never touches a chemical his entire life. He sits in front of a computer and he does these type of calculations and figures out better ways to do that. These red lines are predictions made by a computer. Drawing this molecule on a computer and calculating, and you can essentially predict exactly what color this is going to be. Based on the red lines, I would say it's going to be orange. The molecule itself actually is orange. That's the color. And you do this inside of a computer. You never touch the lab. So you can figure out properties like light emission, drug interaction, reaction pathways, electrical thermal conductivity, protein shapes, whatever it may be. One really important one now that's emerging is protein shapes. In terms of your body, the way your body interacts with the external chemicals is through proteins. These molecules that have a very specific shape, they have binding sites, molecules go in these binding sites, things happen. Well, if you know what a protein looks like from X-ray crystallography, then you can make random molecules on a computer, throw them in there, and see how they're going to interact. You're essentially making a prediction about what's going to happen when I administer a drug to a human being. The better our computers get, the better we are at doing this. So in the future, if you guys go into graduate school 5 years from now, you'll be doing these calculations on your cell phone. Maybe not this complex, but similar calculations on your cell phone. So finally, it's important. I cannot stress this enough. Chemistry, research, science is very, very important. So here's one example. Frederick Wohler, 1828. He's trying to do this reaction, potassium cyanate plus ammonium sulfate to make ammonium cyanate. This is a double displacement reaction. You guys have talked about this. You've talked about equilibriums. Why is this important? Well, he accidentally made urea. Does anyone know why urea is important? You literally flush this down the toilet every time you go to the bathroom. Kind of a useless, simple, stupid molecule. Doesn't really matter. But why was it important in 1828? Because up until this point, people didn't think we could make stuff that the body can make. There was this idea of vitalism, that you needed a living organism. There's some sort of vital force going on that was necessary to make molecules. And he showed by making one molecule accidentally that you didn't need a body to make molecules. Think about how profoundly big that is. Here's his comment in a letter. He said, "I can no longer, so to speak, hold my chemical water and must tell you that I can make urea without needing a kidney." It's actually made in the liver, processed in the kidney, but we'll forgive him for that mistake. But He made it. He made something a living organism can make. This is the birth of organic chemistry. This is the birth of synthesizing molecules to do what we want. Here's one example. Salicin. So for a couple thousand years, we've been chewing on bark of a willow tree. And basically what we want is this molecule right here because it relieves pain, reduces fever, stuff like that. Well, you could get this out of a plant. Alternatively, now we can make it. You can go to the drugstore and buy this by the pound if you want to. And that's aspirin. So because he discovered urea, because he found out we don't need vitalism, you can make things like aspirin. Finally, this one's really important. Ammonia. Does anyone here know what ammonia is for? Fertilizer. Absolutely. Your answer is correct. So, ammonia. Household cleaners, water disinfectants, and most importantly, fertilizers. Well, why are fertilizers important? So if you look inside our bodies, here's a single strand of DNA and a protein chain. If you look inside of this, there's hydrogen, oxygen, nitrogen, phosphorus, all these different atoms. Well, where do these atoms in our body come from? They come from eating plants and animals. Well, animals get their carbon and nitrogen from eating plants. Where do plants get those from? They get their carbon from the atmosphere, CO2. They mix that with water and they make other things. But they also need nitrogen to make plants. Well, you put nitrogen in the ground, that's where plants take their nitrogen from. The more nitrogen available, the bigger the plants can grow, the higher the crop yield, the more plants you can produce. Why is that important? Well, how do we make this? How do you put it in the ground? How does it go from a lab into the ground and you get bigger crop yields? And it's through this reaction. H2 plus N2, you have an equilibrium, it gives you NH3, it gives you ammonia. So let's flash back to 1905. Fritz Haber's hanging out in a lab and he's doing this reaction. He has a little flask filled with hydrogen and nitrogen. He's adding different metals, different pressures, different temperatures, trying to figure out how to make ammonia. Meets up with Carl Bosch, a chemical engineer. 1909, they start making this 80 grams an hour. That's roughly a quarter of a pound per hour. Commercialization by 1913, they're making 20 metric tons per day. Today we have the Haber-Bosch process, making over 100 million metric tons per year. So let's put this into perspective. How important is ammonia? It's arguably the highest impact innovation of the 20th century. Without it, 50% of the world's population would not be here. If you think about it, if you can't make enough food, you can't supply for people, they will not live, they'll die, or they won't reproduce. Half of the world's population owes its existence to Fritz Haber and Carl Bosch, and you guys have never heard their names before. I mean, if we want to talk about importance, it's hard to beat this. And I could go on for days. There's all sorts of discoveries that changed the course of human history. And here's just some examples. Everything from periodic table to electrons, neutrons, electron transfer, plastics, electrolysis, whatever it may be. Huge discoveries. But there are battles still to be won. So I'm not going to go through this list, but basically there's a lot of problems we're still going after. By far, I think the most important is energy research. Energy, if you give me energy, I can do anything. I can purify water, I can recycle any material. I can turn lead into gold. Literally, if you give me a solar-powered particle accelerator, I can turn lead into gold. Energy is the key to all of that. So you guys have heard about energy research, why it's important. They've given you sales pitches like save the planet, energy independence, security, sustainability, and jobs. These are all important reasons. They're very valid. But I'm going to go an alternative route, and I'm going to sell this to you from the sense of innovation. First innovation, or one of the first by mankind, was the harnessing of fire. Today we know this is hydrocarbons plus oxygen giving you CO2, water, and heat. Very simple reaction, but hugely important in humans progressing from caves to where we are now today. Let's fast forward a little bit. 1896, Röntgen takes the first X-ray. That's his wife's hand. You can see her ring finger on it. Jump forward today, 114 years later, we have functional MRI. We can view inside the human body in real time and see what's going on. You can literally see people think with MRIs. That's today. Here's another example, 1903. Wright brothers throw basically a lawnmower engine on a wood frame and get to fly 200 feet. 66 years later, we're on the moon. We flew 200,000 miles and walked on the moon. It took us 66 years to get there. 1890, arguably one of the first computers. This was punch cards. They were trying to do the US Census. They were trying to keep track of people's demographics, money, all sorts of stuff. 121 years later, you have a supercomputer basically in your pocket. Your cell phones are really good at processing information. How do we power this innovation? This stupid reaction. 90% of our energy comes from this stupid reaction. Hydrocarbons plus oxygen, CO2, water, and heat. This is how your car runs. We don't build our cars out of sticks and stones. Why do we power them like we do? It doesn't take a PhD in chemistry to see how ridiculously small our progress has been in energy research. Why are we using the same reaction now that we used back then? Summed up in a quote, Sheikh Yamini, former OPEC oil administrator, the Stone Age didn't end because we ran out of stones. What does that mean? We still have stones, right? We have better options. Same thing for energy. We have better options. It's just a matter of figuring out how to utilize them, how to make them better so everyone can use them. So when you think about these really big problems, you think about the really big people that have solved them. And these are the giants: Einstein, Newton, Marie Curie, Jonas Salk, Charles Darwin. There's thousands of them. You can probably think of a bunch off the top of your head. And here's a quote by Isaac Newton: "If I've seen any further, it's by standing on the shoulders of giants." This is an incredibly dishonest statement. This is not true. He hasn't seen further by standing on giants. He has seen further by standing on everyone. He doesn't just come up with an idea out of nowhere. No, it's based on many little incremental advances. So if we look at the continuum of knowledge, we start out at zero knowledge. Here's knowing everything. If you want to really draw this picture right, it's not giant after giant after giant. It's giant, small discoveries, then a giant, then small discoveries. So the people doing this, yeah, they're huge, they're hugely important, they changed the course of human history, but we also need people to make incremental steps forward.